Freya is a senior undergrad student at Ahmedabad University, majoring in CS and minoring in physics and mathematics. She has previously conducted research in quantum computing at Harvard University, Institute for Quantum Computing at Waterloo University, and then she was recently at Caltech through a summer undergraduate research fellowship. And recently, she also conducted research at ICFO, the Institute for Photonic Sciences in Spain, in the same field, and she aspires to continue working in quantum computing after graduating. So she will share with us her story and the research she has carried out as an undergrad. So Freya, could you please share your screen?
Yeah, sure. Can you hear me?
Yeah. Okay, yeah, your screen is visible.
Okay, great.
Great.
Um, Hi everyone. So my talk is going to be a little different from what you must have heard throughout today. I'm going to be talking a little bit about my experience throughout my undergrad journey, and I'll talk about how I got those experiences, and then I'll talk a little bit about what sort of research I did in each one of them. Um, so I started out with interning at Q World when I had just graduated from high school. And by this time, I had taken some courses on quantum computing. Like there was this 8-month course by IBM and the coding school, and I had also taken some courses with Q World. So I just wanted to share that Q World is a great organization if you're looking to like conduct research, or if you haven't had any experience and you want to see what it is like working there, then you can easily find mentors and conduct great research. They also have like amazing courses which cover in depth, especially if you're a beginner. And they have this Q intern program which opens up applications every year. So it's like very easy to get involved, and you can also interact with others. Um, so the research that I worked on here was eavesdropping a QKD, or quantum key distribution network, using sequential unsharp measurement attacks. So basically, here we looked at one-sided device-independent QKD network, which is basically made up of this quantum steerable correlations. So what this basically means is that in between Alice and Bob, Alice's measurements will affect Bob's state remotely. So it's kind of like an intermediate correlation between entanglement and Bell non-locality, because Bell non-locality is very strong because it violates uh, Bell inequalities, but so it's somewhere in between. And it is like in this paper, it is defined as this fine-grained steering inequality where Bob's measurement uh, is affected by Alice's measurement, and if this is like if this inequality is satisfied, then we can assume that it is a quantum steerable correlation. So like there is this theorem which is known as monogamy of steering, which says that if the state is maximally steerable, then it cannot be shared with any other third party without losing this correlations that Alice and Bob have. But there was this another study that showed that multiple eaves can eavesdrop while still having some positive key rate, but they do not use this sharp or projective measurements, but instead they use this weak unsharp measurements where they do not get like information about the entire state, but they get partial information. So this research particularly focused on finding the number of such eaves that can get this positive key rate, which is still less than the key rate of Bob. So they are not detected. So like Bob does not know that there are multiple Eves getting such information with a positive key rate, but they still have this. So uh, this paper like focused on finding how many Eves can get this sort of information with different key rates. So this was kind of our like the results that we found, where we looked into like 3 different key rates and then the number of maximum Eves that can have a positive key rate, or they can get some kind of information from this without Bob and Alice knowing. So this basically like looked on the security of this uh, one device, like one-sided device independent QKD network. So this was the research I conducted with QWorld. Then during summer of my freshman year or my first year, I got to work with a group at Harvard. So it was like the way I got this opportunity was cold email, which is a little bit unusual. But I had certain different experience as well apart from this Q World internship. Like I was a KISS-KIT advocate, so I had done some projects with under the mentorship of people from IBM Quantum, and then I had some other projects from other different projects like from hackathons and things like that. So I think I just cold emailed and somebody liked my resume, and then they ended up offering me this project. So I started working remotely, but then I was able to visit them over the summer, which was pretty cool. So this research was very different from anything I had done previously because this involved like quantum optics and quantum computing. So um, what I did in this research was we looked at this different kind of platform and we explored if we can do quantum computation with that. So this was basically like a sub-wavelength atomic array, which basically means that the spacing between these atoms is less than the wavelength of light. And in this sub-wavelength atomic array, we have this embedded 3-level quantum emitters. So by 3 levels, I mean then this embedded impurities, which are these red dots over here, they have a ground state, excited state, and also a third state, which we call it as high energy metastable state. And we call it this way because this high energy metastable state does not interact with any other high energy metastable state of another impurity. It only interacts with the excited state of that same impurity. So, and it also has like a very large decay rate. So you can just store any quantum state in this HMS state for a very long time. But it cannot interact with anything else. So it acts as kind of like a quantum memory or something like that. And then this lattice atoms only have like 2 levels, which is ground state and excited state. And this lattice atoms and impurities, they have this light induced interactions between them because of the dipole-dipole couplings. And if this decay rate of these impurities is higher than the lattice atoms, much higher than the lattice atoms, then we can then this lattice atoms act as a Markovian bath for the impurities and they can be eliminated. So what this basically means is that this lattice atoms evolve much faster than the impurities, and hence their dynamics can be eliminated and they act as this effective environment for the impurities. So there's like a lot of math involved in this, which I'm not going into, but because like when we do this Markovian bath elimination, they kind of act as this dissipative bath, which in turn affects the energy levels of the impurities. So when we eliminate this lattice atoms because they move very fast, so in doing that, this impurities behavior is affected in a very strange way, which is that their their decay rate decreases, and hence it makes them very long lived. So this is why like we chose to like take a look at this system. And so if the decay rate of this impurities is very high, then we have a very long coherence time and we can perform a lot of quantum gates and things like that. So this was all based off a previous paper from the same group where they worked out the math and they examined the system. And then my paper focused on looking at how we can implement various quantum gates on this particular system. So mainly like we devised control mechanisms of how like we can apply gates. So this dipole-dipole interactions that I told you that happens between these lattice atoms and impurities, this automatically transfers into an I-swap gate. So, but yeah, so and we also like devised like different mechanisms on how we can apply X rotation and Z rotation gates. So together, this I swap and X and Z rotation, they form universal set of quantum gates, which basically means that using just 3 of these gates, we can implement any sort of quantum circuit or anything on this system, and that means we can do quantum computation. And then we also looked at the fidelities of these gates, and if we applied like 100 I-swap gate operations, then we get error rates as small as 10 raised to minus 3 or 10 raised to minus 4 for different uh, this spacings, which is like smaller than what we get on with superconducting qubits or even trapped ions. But note that the study is entirely theoretical, and these are just theoretical calculations. And in fact, like experimentally, it's very hard to implement this kind of sub-wavelength atomic array. And then we also like talk about how we can like detune these impurities. For example, like if we have 3 impurities in our system, and if we want to apply like operations only between 2 of those impurities, so we need to like detune this third impurity so that whenever we apply like a driving field or anything, then this third impurity does not get affected. And then this third impurity could be in ground state, or it could be in excited state, or it could be in any arbitrary superposition state. So we talk about like different ways on how we can like detune this or like control this impurities. So that is also very important. And so yeah, mainly this paper talks about all of these control mechanisms. And then as a proof of example, we also implement this 2-qubit and 3-qubit entangled state, which is GHZ and Bell state on our system with particularly high fidelities. So just to show you like some plots, for example, here we have applied like 700 X and Z gates sequentially in our system, and we get like pretty high fidelities for that. And then this is how like an X gate looks when we apply on just one system, and then the other so this is like a 2-qubit system, and one of them is just detuned, and we apply X gate only on one of them. So the excited state goes down, and like the excitation goes to the ground state. I mean, the photon goes to the ground state. And this is like another graph for applying a Z gate in our system. And this is the plot for the error rate where I showed you the numbers before for like the error rates here. And then this plot basically shows how we implement this Bell state and GHZ state into our system. So for Bell state, we implement like a square root I swap and then C and gate and X gate. So this basically shows where the population lies when we apply each of these operations. And then here, like as you can see for GHC state, we first have to create Bell state between two of these qubits. So we repeat these operations, and then there's whole lot of other gates that we apply. And then we talk a little bit about what sort of atoms we can use to make such a system experimentally, which is like strontium and deuterium. But yeah, you can, like, if you're interested into something like this, you can read more about it in this paper. And yeah, if you have any more questions, you can ask me later. Then in the summer of my sophomore year, in the summer of my second year, or sophomore year, I visited Institute of Quantum Computing at University of Waterloo, and they have this really cool program which is called USQUIP, which is a 2-week summer school, primarily aimed at undergrads, where they teach you theoretical and experimental study of quantum information. And there are people coming in from all over the world, and they're like 30 to 40 students. And you learn a lot of things because they, like, you can do, like, they teach you how to do some of the experiments there in person. So it's very cool, and you get to experience all of these different hardwares that are going on right now, like superconducting qubits or trapped ions or neutral atoms, and you kind of get to see all these setups in person and how all of these labs function. And then after this 2-week summer school, they also offer like this undergraduate research assistant fellowships for like another 8 to 10 weeks for students to just work there under a faculty advisor. And yeah, so it's really cool, and the applications open up typically in December and January for anyone who might be interested. Um, so again, at IQC, I kind of wanted to try experimental stuff. So I was working with a QKD lab, which so it's called basically the KeySat mission, and that group primarily works on this. So what this mission aims to do is it aims to demonstrate QKD between ground station and a satellite, and they have the ground stations across Canada and also internationally, I guess, a few places in Europe. And they already have like a satellite that they have launched, and they did plan to demonstrate in sometime in 2025. I'm not exactly sure if it's delayed or not. But this is an association with Canadian Space Agency as well. So my work in this experience mainly involved working with things that were needed in this mission. So it wasn't exactly like a concrete project, but instead it was like several small tasks that I had to do for different things that were needed. And it was like theoretical and experimental both. For example, like determining which mirror coating materials to use such that there are as less polarization aberrations possible, or like how to place the mirrors in the telescope, or which geometry to place them in such that we can correct this polarization aberrations or reduce them. I also had to conduct like SNR and power calculations for the telescope such that we can know what power of the telescope to get to like detect the signals. And also just to I conducted like light pollution calculations on the ground station. And then also uh, test their satellite tracking code to see if the satellite functions the way it's supposed to be with the code. And they had this new piezo motors in the lab, so I had to write some code to make it compatible with their software. So there were like a lot of different things, like small tasks that I had to do. But it was very interesting to see how theory and experiment like blend together, and how like how such a real life implementation happens. Yeah. So after this, in my junior year, I visited Caltech as a surf student. So basically, the surf program, the full form is Summer Undergraduate Research Fellowship, and this is mainly for undergrads to conduct 10 weeks of research under a Caltech professor. So this is kind of like a fellowship that they give you to come there and conduct research. And the way, so to get into a surf, you basically have to contact faculty members or even grad students from Caltech around like from September to December every year. And you can like you obviously contact people whose research you're interested in, and you tell them about the things you have done and what sort of project you have in mind. So if they like your project, then um, yeah, they like set up a meeting and everything. But this is they do have a proper application as well, but mainly you first have to like cold email them and then only apply through the application. Um, so yeah, in here at Caltech, I was actually working in an AI research group, which was not quantum, but the entire group was mainly working on AI. But my project was using this AI for quantum applications. So I specifically used this Fourier neural operators to learn dynamics in quantum spin systems. So um, Fourier neural operators is basically neural operators, and they kind of like learn they are PDE solvers basically, but they're different from the traditional or the conventional PDE solvers, because the conventional PDE solvers will only like learn one instance of the PDE that you give them, but neural operators, instead of like um, learning just this one PD, they learn the entire family. So it basically means that they learn the underlying function rather than just uh, like, yeah, they learn the underlying function. And another thing is they're also resolution invariant, which means that you can train them on a coarser grid, and you can then test them on much finer grid, and they'll still give you like there won't be any reduction, like they'll still perform the same. They'll be still that same efficient. There won't be like any more error rates or anything like that. And they're also like slow to train but very fast to evaluate, and even on such finer grids. Um, so in this project, I basically use this Fourier neural operators to for a problem that is particularly hard, which is simulating quantum systems. And this is hard computationally, because we know the size of like this uh, like quantum operations, they happen in Hilbert space, and which grows exponentially, and hence it can be very computationally hard to simulate it with growing number of qubits. And it is also hard experimentally right now, because we do not have the hardware that I mean, we do not have that much qubits, or the qubits, they might not have that much coherence times, due to which we may not be able to like simulate it for much longer times than what we want. So this could be like interesting, because FNO could learn this patterns in the I mean in the dynamics data that we provide them, and then it could extrapolate it to later time scales that might not be possible right now experimentally or computationally. um, so for this we use like a 1D Heisenberg spin half Heisenberg model, um, where this S SIs are like the spin operators and X, Y, and Z bases. And then this J terms are like the interaction terms between them. And then this is like an external field. So like this is a very standard model in quantum spin systems, but we particularly use this. And then we had like two different approaches. One was the wave function approach, where we provided FNOs with the entire 2 raised to n wave function of our quantum system, and then it would like learn it will learn the patterns. And as you can see in this figure, the data that we provided was this uh, like the dynamics of this pi time over here, and then this later is like the extrapolated time that FNO extrapolated on its own after learning the patterns of the training data we provided. And it does, we tested out with 4 and 8 qubits. This plot is for 8 qubits, and it does like pretty well with our input, where the fidelity stays pretty high. And then this we like did like benchmark, like we compared it with another ML model, which is UNet, and it does not perform that as well as FNO, especially with something called the low energy inputs, which I'm not going to talk about due to time constraints. But this approach may not be that practical because you have to give like the entire 2 raised to n wave function, but this we kind of did as a proof of concept. But the really interesting case is this Hamiltonian observables, where we do not give it the FNO the entire 2 raised to n wave function input, but we only give it like some observables, which is basically just expectation values. Um, and then it kind of extrapolates it to up to twice the duration of the training period. So in this plot is for like 8 qubits, and this gray region is the extrapolated time. So using like this Hamiltonian observable, we were able to like uh, extrapolate it to twice the duration of the training period with a relative error of 6.46%. And we also achieved like a substantial 6.71 times speed up with FNOs compared to exact unitary evolution for inferring this dynamics at later times. For this was for like 8 qubits, and with only like a minimal fidelity reduction of 0.04%. Um, so yeah, this was like a glimpse of the research I conducted at Caltech, which was very computational, as opposed to the research that I conducted previous to that. And then in this past December and January, I was at ICFO, which is in Castelldefels, Spain. And this it's like a research institute where they primarily work on photonics. Um, and they also have like a lot of different research fellowships for undergrads, masters, and even PhD students. And it's like runs throughout the year because they have many different fellowships. I particularly received like this Maria Zuel fellowship, which is particularly for women, and uh, they basically give you like a stipend, and you can come anytime you want throughout the year. So it's like very flexible. But yeah, like if you're interested, you can check out all the other fellowships that they give on their website. Um, and I like kind of worked on estimating quantum channels using classical shadows over there, but I won't talk about it because of the time constraint. And then I have this some helpful links that you can see to kind of see other like see what kind of opportunities are there, and if you like want to apply or anything like that. But yeah, that's my presentation, and let me know if you have any questions or anything.
Thank you, Freya, for this one talk. I believe this will be very helpful, at least for UG students. As for questions, I believe we don't have any questions, but if you have any questions, you can post it or you can also email us later on.